Hello everyone. In this video I'm going to create a new playlist on my channel that will be about stereochemistry, and we will be discussing stereochemistry from the basics, and then we will go towards advanced level, towards MPhil and PhD level. We are starting from college or BSc level, bachelor's level, honors level. So this is a very introductory lecture about stereochemistry. We will cover all the basic definitions, terminologies that are most commonly used in stereochemistry, and this will be a new playlist on my chemistry YouTube channel. If you are unfamiliar with my YouTube channel, then let me remind you that I have made several playlists on my YouTube channel regarding chemistry, particularly organic chemistry. One is about organic chemistry general, where I have discussed general concepts, and if you are more interested in organic chemistry name reactions, then there's a separate playlist about name reactions. And if you are interested about to know retrosynthesis, then there's a separate playlist about retrosynthesis. And if you want to know about spectroscopy, then there's a separate playlist about spectroscopy on my YouTube channel. So in stereochemistry playlist, this will be the first video of that playlist. Definitely I will make so many videos about stereochemistry and the reactions that involve stereochemical relationships over a period of time, but this is the beginning of a new playlist. Okay, let's start with the stereochemistry. So it's a chemistry of molecules in 3 dimensions. We can simply say that. So let's start from very basics, that how we can understand these molecules. Consider 2 compounds we produced while finding all of the isomers of these compounds, C7H16. So this is a molecular formula, and this can have number of structures, number of isomers. So for example, 2-methylhexane is an isomer of 3-methylhexane, and 2-methylhexane is a superimposable with its mirror image. So we are writing Me for methyl and Bu for butyl, and if we swap these methyls from left side to right side, and if we swap these hydrogen and butyl from right side to left side, they become mirror images of each other. And if we rotate this compound, and it's superimposable. So if you put this structure with this one, this structure on top of this one, they will be exactly same. Alright, hence they are superimposable mirror images of these in this compound. Okay, so this is how we define superimposable mirror image. The purpose of this slide is to teach you that how we can say which one is a superimposable mirror image. So this is an example where it is shown that how this compound is superimposable image. Okay, let's move on to the next slide to learn further. And consider 2 compounds we produced while finding all the isomers of C7H16. So this is 2-methylhexane and 3-methylhexane, and these are again superimposable mirror images. So this is Et is ethyl, Pr is propyl, and Me is methyl. So if we swap these structures from left to right, so the ethyl from left goes to right, and methyl from left goes to right, and this propyl from right goes to left, and this hydrogen from right goes to left. And if we further rotate this compound, then these top one and this bottom one are superimposable with its mirror image. So this is really important. If you want to learn further more about stereochemistry, you should be familiar what is superimposable mirror image. Okay, let's go on further. Compounds that are not superimposable with mirror image are called chiral. That's why superimposable mirror image concept was important, which we discussed in previous slides. So if the compounds are not superimposable with their mirror image, they are called chiral, and the chiral is a Greek word which means handed. So 3-methylhexane is a chiral molecule. Compounds that are superimposable with their mirror image are called achiral, like 2-methylhexane is an achiral molecule. An atom, usually carbon with 4 different substituents, is called a stereogenic center or stereocenter or chiral center. Okay, these were the definitions: what is chiral, what is achiral, what is stereogenic center, what is stereocenter. Further on, we will discuss more in detail about these terminologies and we'll explore much more about stereochemistry in subsequent slides. Let's move on to next slides. Now, next basic definition in stereochemistry is enantiomers. So 2 compounds that are non-superimposable mirror images of the 2 hands are called enantiomers. So consider this structure 3-methylhexane. If you write down this structure in this one, ethyl on top, methyl on this bottom, and then propyl and hydrogen, and you put mirror for this structure, literally mirror. So what mirror will show you? These ethyl and methyl on the right hand side, and then propyl and hydrogen on the left hand side. So these are called enantiomers because there is a chiral center. One thing, compound, if any molecule or if any compound is called enantiomer, then it must be a chiral first of all, and then it must be a non-superimposable mirror image. So in this 3-methylhexane, these 2 compounds or these 2 conformations or these 2 structures are called enantiomers because they are non-superimposable mirror images of each other. So this is how we define enantiomers. Okay, let's move on to next type of stereoisomeric conformation, that is structural isomers. So compounds of the same molecular formula with different connectivity are called structural isomers. See, for example, the functionality, connectivity of these compounds, 2-methylpentane and 3-methylpentane, they all contain same number of hydrogens and same number of carbons, but they are called structural or constitutional isomers because they differ in the connectivity of atoms. Look at this first one. In this one, methyl is at 2 position, and in this one, methyl is at 3 position. Rest of the structure is same. They are alkane. They do not contain any functional group. They are saturated hydrocarbons, but the connectivity is different in these 2 molecules. However, these 2 compounds possess same molecular formula, same molecular weight, same number of carbons and same number of hydrogens. Next type of isomerism or stereoisomerism is conformational isomerism. The conformational isomers, we will discuss the cyclohexane conformational analysis in detail in next videos hopefully. And so we define conformational isomers as compounds of the same structure that differ in rotation around 1 or more single bonds. So conformations are possible in all single bonds. They rotate freely around its axis along the single bond line. So these are the couch conformations. We call couch conformations. So this is a Newman projection where we have a front carbon and below that there's a back carbon. So this front carbon contains methyl and couple of hydrogen, and so as the back carbon contains methyl and 2 hydrogen. So these 2 compounds are conformational isomers because they differ only by their conformations. Okay, what are the conformations? We will look upon conformational isomers in more detail in next video. In this basic video, we are all just touching the basic definitions, basic concepts. Let's move on to the next example. Next is called configurational isomers or stereoisomers. Compounds of the same structure that differ in 1 or more aspects of stereochemistry. How groups are oriented in space. Enantiomers are diastereomers. So we haven't discussed diastereomers so far, but in next few slides we are going to discuss what are diastereomers, but we definitely discussed enantiomers. Enantiomers are compounds which are non-superimposable mirror images of each other, and they must be chiral. So if you look at these compounds, they are enantiomer of each other and they are configurational isomers. So what is configuration? It could be R or S configuration according to Kahn-Ingold Prelog rules. These are short form abbreviated as CIP rules, CIP CIP rules. Okay, let's move on to these CIP System Revisited. So there are certain rules before we start applying this system to compounds. So number one is rank each substituent attached to stereocenter according to CIP priority system. 1 will be the highest and 4 will be the lowest. So this numbering shows that position 1 contains the highest priority, and 2 second most, third one, and the fourth is the lowest one. So 1 being the highest and 4th being the lowest. Okay, next rule of CIP is view the compound with the lowest priority substituent pointing away from you. So for example, if this compound is 1, 2, 3 and 4, we can write this compound, this 2 is CH2 and CH3, we can write it as ET, ethyl, and 1 is propyl, CH2, CH2 and CH3, we can write PR, and then is this one. So this is how we can transform these compounds, where we can push the 4th priority into the lowest line, okay, the dotted line. Okay, rule number 3 is draw a circular arrow from connecting substituents 1 to 3 from highest to lowest priority. If the arrows move clockwise, the stereocenter is labeled R, that stands for rectus. So R means rectus. If the arrow moves counterclockwise or anti-clockwise or anti-clockwise, then the stereocenter is labeled S. This stands for sinister. So this compound, where we have 1, 2, 3, 4. Now if we start from 1, going from 1 to 2, and then go from 2 to 3, so it's a counterclockwise, it's an anti-clockwise, so we will write S. And if we go from this way, if the first priority is PR, so the larger the chain, higher will be the priority, or higher the atomic number, higher will be the priority. Okay, so we will learn more in next examples where we can assign the priority on the function number of atoms. So if you see here, simply propyl is a bigger chain than ethyl, so we will assign propyl as number 1 priority, and ethyl contains just 2 carbons. That's why we are assigning ethyl as priority 2, and methyl just contains 1 carbon, that's why it's 3 priority. But what happens if there are no carbons, or if there are heteroatoms? So we will assign according to their atomic number. So higher the atomic number, higher will be the priority. So if you look at this example, so PR gets the number 1 priority, and ET gets the number 2, and methyl gets the 3. So 1 goes to 2 and 2 goes to 3. So this is a clockwise, and it's R. So this one is R clockwise, and counterclockwise or anti-clockwise is S confirmation. So these two compounds, S3-methylhexane and R3-methylhexane, are said to be configurational isomers. Okay, let's move on, and let's apply these CIP systems to number of molecules. Now if you look at this structure, we have ethyl 2 carbons, and we have methyl, and we have heteroatom. So fluorine definitely has higher atomic number than carbon, so fluorine will get the number 1 priority. Hydrogen, just atomic number of 1, will get the least priority of 4. And compared to ethyl and methyl, so methyl will get 3 and ethyl will get 2. So if we start from 1, we will go towards 2, and then from 2 to 3. So it's a clockwise rotation, and that's why we will say this is R. If you look at this example, now first of all identify the chiral center, identify the stereogenic center. So how you can identify stereogenic center? It's a center which is connected with 4 different group of atoms. So if you see here, number 4 is hydrogen, number 1 is this bulky terbutyl group, and number 2 is double bond side, and number 3 is single bond side. So if we want to assign the priority, so this we have to compare now. In this position there is a C, and there is also a carbon, and there is also a carbon. Now what happens next is we see that this is a tie. We cannot decide which is going to be a number 1 priority, because all these positions contain carbons. Okay, now next is, if we further move, then this contains carbon, and if we further move, this also contains carbon. Okay, then if we further move here, this also contains carbon. So still we cannot decide, because all of these positions contain carbon, so the competition is tied. And the next is again carbon. So if we go here, next is again carbon here. From this side is also carbon. But if we go further, there's next is carbon, but there here we are finished with carbon, we have hydrogens here. So that's why terbutyl, being a big group, or wins the competition of priority. That's why we call it number 1. Hydrogen being the lowest in atomic number, we call it number 4. And the double bond side of this cyclohexane ring contains priority number 2, and the single bond side contains priority number 3. Now if we rotate from 1, if we start from 1 and then move towards 4, we will see that it's a S conformation. Let's move on to the next structure. So this is 1 bromine, 4 is hydrogen, 2 is this long chain, and 3 is this methyl. So if we start from 1, 2, 3 and 4, so this is S conformation. Why we are saying bromine is 1 in priority? Again, because of atomic number being higher than carbons. And why this side is number 2? Because it's a longer chain. It contains number of more than 1 carbon, and this is 3. And hydrogen is always number 4. And again, let's apply the CIP rules to this compound. So number 1 will be oxygen, because oxygen is higher in priority than carbon, because oxygen has higher atomic number. Carbon has 6 and oxygen has 8 atomic number. And one can argue that this carbonyl compound also contains oxygen. Why it's not called priority 1? But if we look closely, then this carbonyl compound first contains carbon, then it contains oxygen, but this hydroxyl group directly contains oxygen. That's why we will put priority number 1 there, and the number 2 priority will go to aldehyde carbon, and number 3 to this ethyl, and number 4 to this methyl. And it is not necessary that we should always have hydrogen as 4th priority. We could have another group which is least in atomic number, which is least in size maybe, then that could be our 4th priority, and that should be on the dotted line. So 1, start from 1, go to 2, and then go to 2, from 2 to 3, and then go to 4. That is R configuration. That is R rotation, that is clockwise rotation. That's why we are saying it's R. Okay. If you don't understand any of these examples, please let me know in the comments, then I will explain more in next video in case if needed. Okay, let's move on to this example. Chiral objects can only be recognized as chiral by another chiral object. So this is a carbon. Okay. Now this carbon can be S and R. So the S conformation will smell differently and R conformation will smell differently. So these two compounds, they just differ in their configurations, but they show different properties, okay? And your nose can tell because they can smell differently. So R has a different smell and S has a different smell. You can smell these compounds. So number 1 priority is this, and goes to 2, and then 2 goes to 3, and number 4 is hydrogen. So this is a clockwise rotation, that is R. Now if you see here 1, then number 2 is this one, and 3, and this one 4. And now this is anti-clockwise, counterclockwise, this is R configuration. So what happens when we have multiple stereocenters? Before we discussed when we have a single stereoisomers. Now we are going to discuss when we have more than one stereocenters. So if we have one stereocenter, then there are 2 stereoisomers possible for that compound. For example, this is one stereocenter present in this whole structure. That means there could be a 1 enantiomer of this molecule possible. Then these 2 are called 2 stereoisomers. If we have 2 stereocenters, then we could have 4 stereoisomers. So one is this one, S and S. Second is RS, then SR, then RR. So the 4 stereoisomers are possible when we have 2 stereocenters present in the compound. Okay, when we have multiple stereocenters, then they could be enantiomers or diastereomers. Then we have to identify the relationship between compounds. So this is, we have to do configuration. It is R or S. Definitely it is S, and this is also S, and this one is R, and this one is R. So this compound, left hand compound side and right hand compound side, are enantiomers to each other. Now if we look at the bottom one, this is R and this is S, and this is R and this is R, and this one again. So these bottom and top are enantiomers, but what about others? So stereoisomers that are not enantiomers, non-superimposable, are called diastereomers. So the relationship between these blue lined arrows is diastereomeric relationship between these two compounds. So where you have for example, you have a 4R same configuration, but you have a different configuration at one stereocenter. Okay, that is why this one blue arrows shows these two are diastereomers. Okay, similarly, if we see this one, we have a 3S and we have 3R. So the configuration is changed at position 3, and if we see here at position 4, it is 4S, and this one is also 4S. So the configuration hasn't changed at position 4, but it has changed at position 3. Hence the relationship between these two structures is diastereomeric relationship. We will say that these two compounds are diastereomers to each other. But if you see in enantiomers, you will see that the configuration between two stereocenters is completely changed. So this is 3S and this is 4S. So this becomes 3R and 4R. If you look at the bottom one, this is 3R and 4S. And if you look at the right hand side, this is 3S and 4R. So there's a difference between their stereoisomeric compounds. So 3S and 4R, and this is 3R and 4S. And now if you compare these top and bottom, or if you compare these blue ones, you will see that the configuration is different on only one stereocenter, not on both. If the configuration is different on both the stereocenters, that will be called enantiomers. If the configuration is changed only at one stereocenter, that is called diastereomers. Okay, this is called a diastereomerism. Okay, let's move on to the next. Now if we have 3 stereocenters, then we will have 8 stereoisomers. One possibility is RRR, and then SSS. Then next is SRR, then RSS, then RSR, then SRS, then RRS, then SSR. The quickest way to find out how many stereoisomers will be possible for a certain compound which is chiral, the molecular formula is 2 power n. So if the stereoisomers are 3, stereoisomer contains there are 3 stereocenters, then we will put the value of n equals to 3. Then we will multiply 2 times 3, and that will be 2 times 2 is equals to 4, and then 4 times 2 is equals to 8. Hence, if compound contains 3 stereocenters, that is going to have 8 stereoisomers. That is the formula 2 power n. To find out quickly how many stereoisomers will be possible. Okay, let's move on to the next, multiple stereocenters. Now we have to find out the relationship between the molecules. What is the relationship between these compounds? So if you look at this one, there is a plane of symmetry going through this one. This is same compound, superimposable, but this one is different. These are enantiomers. They differ on both these stereocenters. If you see here, this is 3S and this is 4S. And when we write down another enantiomer, the configuration must change at the stereocenters in order to be enantiomers. 3S must become 3R, and 4S must become 4R. That's why we call these two compounds as enantiomers. Okay, let's move on to next slide. What are the meso compounds? So far we discussed enantiomers, diastereomers, constitutional isomers, configurational isomers, conformational isomers. Now we are discussing meso compounds. So meso compounds are those compounds which do contain chiral center, but they are not chiral because of the plane of symmetry. So what is plane of symmetry? If you cut this compound from middle, both the sides, left side and the right side, become equal, become identical, become very similar to each other in terms of connectivity, in terms of number of atoms, in terms of number of hydrogens, in terms of number of carbons. So if you cut this compound into pieces, into two pieces, so the left side piece and right side piece become equally identical. Whereas in enantiomers, if you cut the molecule, they are not equal because of their configurational status. Their configuration is different at different stereocenters. So the configuration at 3 and 4 stereocenters is S, but if you write down its enantiomer, the configuration will become R at both these centers. That's why we call these two compounds as enantiomer. The relationship between two compounds is enantiomers, and the relationship between these two compounds is Meso compounds, and Meso compounds are achiral, okay, even though they contain chiral centers. So they contain, this is a plane of symmetry. Furthermore, explaining, this is a plane of symmetry which cuts the molecule and divides this molecule into two pieces, and those two pieces become identical to each other. Whereas in enantiomers, there is no plane of symmetry exists. Okay, let's move on to next. This is called a racemic mixture, where we have a 50% of one enantiomer and 50% of another enantiomer. So 50-50%, 50-50 ratio of two enantiomers is called a racemic mixture. It's also known as racemate. For example, you have a E2-butene. It's achiral because it does not contain any chiral center. If you have a double bond, then there can be no chiral center. If you do HBr addition, then HBr will be added across this double bond, and you will now get a chiral bromobutane. Now this chiral bromobutane will be obtained in 50% S and 50% R. So the net result will be the racemic mixture, and this is called a racemate. So next, move on to the racemic mixture in medicine. So S-ibuprofen is active and R-ibuprofen is inactive. So the stereoisomerism or stereochemistry is really important in medicinal chemistry, because one stereocenter can change all of the properties of compounds in terms of medicine and make it active as a medicinal compound or inactive as medicinally inactive. Let's move on to next example, where this thalidomide, which was worldwide used from 1957 to 1961 for morning sickness and as a sleep aid, but then this caused severe side effects in the childs, and then this drug was banned in the Europe. Now if you see this one, R isomer of this thalidomide is analgesic, but S thalidomide is teratogenic. So just change in the configuration at the stereocenter alters the altogether properties, medicinal properties of the compound. Just by changing the configuration, just by altering the configuration at the stereocenter, completely changes the configuration properties of the drug. Okay, let's move on to the optical rotation and polarimetry. So it's a polarimetry is a technique that measures the polarized light passing through a sample, and it gives us idea that whether or not this compound is optically active or not. So what happens is we have a monochromatic light source, and then randomly oriented light, and then optical polarizer that allows vertical light to pass through, and then optical polarizer only allows horizontal light to pass through and no light emitted. Let's discuss further. Chiral molecules will rotate polarized light either in left side or right side. So we have a monochromatic light source, then randomly oriented light, and then optical polarizer only allows vertical light to pass through, and then we have a chiral material. Now this will be detected at the detector. Either it will be a left hand side or it will be a right hand side. If it's a left hand side, we'll call L. If it's a right hand side, we will call D. So most commonly you might have seen that D glucose available in the chemist shop. So D means the dextrorotatory, the glucose that is there, which is present in that back, is a isomer which rotates the plane polarized light towards the right hand side. That's why we are calling it D glucose. Again, this is a similar phenomena explained. We have a chiral center which measures optical rotatory, and then again the maximum signal will be obtained. This optical rotation polarimetry. Now this is really important, that is percentage EE, that is enantiomeric axis. So sample rotation, single enantiomer rotation times 6 times 100. So using this formula we can calculate enantiomeric axis. The optical purity of substance can be measured by comparing the optical rotation of the sample to the known optical rotation of a single enantiomer of that compound, and the amount in degrees that a chiral material will rotate light is called the optical rotation. So these are some key vocabularies that we learned in this video lecture. One was R and S. Identify the configuration of the stereocenter using the CIP CIP priority system. Then D, a plus indicates that a chiral compound rotates light in a clockwise direction, plus or minus. This has no correlation with S or R. And then L means minus, indicates that a chiral compound rotates light in a counterclockwise direction. This has no correlation with S or R. D, L or plus or minus, or RAC indicates racemic, 50% one enantiomer and 50% another one. Now next question is how we can resolve these enantiomers. Okay, if we have racemic mixture of enantiomers, say for example R compound is X and S compound is X, so both are present in 50-50%. Now what we will do, we will react or somehow associate with R compound Y, single enantiomer. Then we will have R compound X, R compound Y, then X compound X, and then R compound Y. A mixture of diastereomers, okay, because RR then SR. Now converting the racemic mixture first into diastereomers, that is the first step. Next step is separate by some technique such as chromatography, crystallization or distillation. I haven't made videos about these separation techniques, but soon I will make videos about separation techniques on my YouTube channel. Sorry, I took a sip of water. Now let's separate these diastereomers. And if we separate this diastereomeric mixture, one side becomes S compound X and another compound becomes R compound Y, that is single diastereomer. And then another side becomes R compound X and R compound Y, that is another single diastereomer. So somehow remove compound Y. Now we don't need Y because in our mixture we had X compound X. So we remove Y either by different separation technique in order to get single enantiomer. This is how we resolve the enantiomer. Okay, so the technique for resolving enantiomers is we start from racemic mixture, we convert it into diastereomers, and then we convert diastereomers into single diastereomers, and then we convert single diastereomer into single enantiomer. Okay, let's move on to real examples, resolution of enantiomers. Now we have a S2-chloropropionic acid. We want to resolution of this enantiomer. Then this nitrogen lone pair is basic, so we will make a racemic. So RS diastereomer of this salt. Now we have a RR diastereomeric salt, RS and RR. Now RS goes to become under acidification to give you this S2-chloropropionic acid, and then R-chloropropionic acid gives you this compound, and then we separate this diastereomeric salt into single diastereomer, and then we acidify to get our desired enantiomer. In the last, this is a tip, or this is the extra thing that I'm gonna tell you, but we will discuss in more detail about this sort of situation or these sort of systems where we don't have any chiral center, where we don't have a stereogenic center. That means the compound is still chiral, but it does not contain 4 different groups or 4 different atoms, but still it's a chiral. So for example, these biphenyls are called chiral because of this is hindered rotation around this bond. These are called chiral, and these are also spiro compounds or chiral, and this one is also aromatic. They do not contain any chiral center, but they have a mirror plane and they are still chiral. So these allenes are chiral also. How they are chiral? and how we can discuss when we don't have any apparent stereocenter, stereogenic center, but compound is still chiral. What does that mean? We will discuss these examples in next advanced level stereochemistry lectures. But next on, I will try to collect questions related to stereochemistry from different organic chemistry books and then solve those questions and make videos on those, so that you can better have practice about stereochemistry. But still we are missing so many stereochemistry topics such as Fischer projection, Newman projection, Sawhorst projection, and different conformations of cyclohexane and cis-trans relationship in cyclohexane. So we have to do conformation from Fischer projection to Sawhorst, and Sawhorst to Fischer projection, or Newman to Fischer projection. So interconversion of the conformations, and then we will discuss the chemistry of sugars. That is also stereochemistry, but that is also contain number of stereogenic centers. So this playlist will grow up. I will make more videos about stereochemistry. Keep watching my channel. Thanks so much. Bye. Take care.